Hi, we're going to look at the math behind flow and Bernoulli's equation. We're going to start off by defining a quantity known as flow rate, and I'm going to abbreviate that with a FR. Flow rate is defined as the volume of fluid that passes a particular point per time. Okay, so since it's a volume, it would be in meters cubed per second. Kind of like a volume speed in a sense. Now that's one useful way to look at flow rate. Another very useful way to look at flow rate is to look at it in terms of maybe like a pipe or something, because often we move fluids through pipes. And what we're going to do is we're going to break this pipe up into a little chunk. Okay, so this is a smaller chunk of fluid inside the pipe, and the pipe has a cross-sectional area, so this chunk of water has a cross-sectional area. And I'm also going to kind of label a distance that represents the height of this cylinder of water. And the volume of this cylinder would be this area times this height. And so if I take my flow rate definition and substitute in for volume the area times that distance over time, what I see is I've got this delta x and this t here. I can combine those because delta x over t was our previous definition of velocity. And so another way to think of flow rate is not just volume per time, but area times velocity. So the area, cross-sectional area of this pipe times the speed that fluid flows through this pipe. Both of these are useful because we have this idea called continuity, which basically says that if I'm dealing with something that's incompressible like a liquid, say for instance water, any water that comes in this side of the pipe has to push an equal volume of water out this side of the pipe in an equal amount of time. In other words, if I shove a gallon in here in the space of a minute, a gallon's going to come out this side in the same space of a minute. We can write that as an equation and say that the flow in equals the flow out. There's a bunch of different applications of this. One of the applications of this, and by the way, when I say flow, I mean flow rate. And I could put volume per time in for flow. I can put area times velocity in for flow on either side. And what are you talking about? Well, what I'm talking about is what if we had a situation where we had a pipe that narrowed. This is what happens when you put a nozzle on a garden hose. According to our continuity equation, flow in equals flow out, the flow rate in this side equals the flow rate out this side. This is a smaller opening. This area, I'll call it area 2, is less than this area 1. If the same amount of water is going to come out this side in the same amount of time, because it's got a smaller area to squeeze through, it's going to have to come out faster. It's kind of the reason that if you take your thumb and put it over the end of a garden hose and constrict the area, it shoots out faster and farther. In this section of the pipe, we have a certain speed, and in this section of the pipe, we also have a different speed. If we write the flow in and flow out as an equation, substituting our little flow rate for both sides in there, we get this. And this is a simple proportionality. If this area here was half the size of the area 1, then the speed would have to be double in order for that to be true. And this is pretty useful. Just note that it doesn't have to be area times volume. I could write something like area 1 times volume 1 equals volume, 2 over time. As long as you're substituting in one of these two flow rate expressions on both sides, you can set up this equation any way you want to. Now let's take a look at Bernoulli's equation. Bernoulli's equation is basically just a statement of conservation of energy. If you were to take Bernoulli's equation and multiply every single term by volume, you'd wind up with a statement of conservation of energy. I'll show you what I'm talking about. I'm just going to do the left side of this equation because the right side is identical. If I take pressure times volume plus density times volume times G times H plus 1/2 density times volume times V1 squared. In every case you see density times volume, you might recall that we said many, many times now that mass is density times volume. So these terms would become mass and pressure being defined as force per area. If I multiply that by volume, recalling that we defined earlier a cylindrical volume was, whoops, I lost my equal sign there, area times delta x, we would have that force over area times delta x, and these guys cancel, and you wind up with force times delta x. Hopefully that looks familiar to you. That's the definition of work. We wind up with work, which is an energy term, times mgh, which if you recall is potential energy due to gravity, and 1/2 mv squared, which is kinetic energy. So this is just a statement of the total energy in one place, the total energy in another place. Bernoulli's equation isn't something brand new. It's just a fluid application of conservation of energy. So how can we use Bernoulli's equation? What are some applications? One might be to look at a system of pipes, maybe in a house where you have a two-story house, and the pipes, some are upstairs, some are downstairs, so we have this kind of change in height going on. Imagine that the pipes are all closed and there's no water flow. If that's the case, we have a certain amount of pressure up here and a certain amount of pressure down here. The heights of the two levels of the pipes are important. I'm going to call the bottom height 0, just like I used to do when I was doing conservation of energy problems back in our previous unit. What happens is, since there's no fluid flow, the terms that have velocity in them, they disappear because they're zeros. I've also made this potential energy term equal to 0, so I wind up with P1 plus the density times G times height 1 equals P2. Everything else went away. And if I solve that for the difference in pressure from top to bottom, which generally we're far more interested in than absolute pressures, we wind up with something like the difference in the pressures just equal to the density times G times height. If you recall, that is that was the equation we came up with for pressure at a depth. Bernoulli's equation reverts back to that when there's no fluid flow. So you might think, well, why do we even need this equation then? Well, if there was fluid flow, we could incorporate that into our problem as well. And that's pretty useful. Another application of Bernoulli's equation could be if you had the same situation we looked at before when we were talking about fluid flow, where you have a pipe that changes diameter. In this situation, we have a couple different areas. We'll call that area 1 and area 2. And we're going to have a couple different speeds. We learned that it would speed up as it went through to this area. What's also going to be true are there'll be different pressures here. Like you learned in the conceptual video on Bernoulli's principle, you learned that when fluid flow increases, or when fluid speed increases, pressure goes down. Well, we would have a pressure in this area and a pressure in this area. Using Bernoulli's equation, first of all, the height, if this pipe is laid horizontally, then there is no height change, and we can ignore the terms that involve height, and we would just have this, which is saying that the pressure difference is mostly due to the kinetic energy difference. It is due to the kinetic energy difference in this case. In a typical problem, instead of giving you both of the speeds and say solve for the pressure difference, you'd probably be given both of the information you'd need to find the areas and maybe one of the speeds, which is not a big problem because then we can use our continuity equation to solve for the other speed and then use our Bernoulli equation to solve for the difference in pressure. Of course, you can solve this equation for any variable in here. These are typical application problems that you might encounter. Can't discuss them all here, of course, but you'll get plenty of practice in your worksheets.